Close your eyes and imagine looking up at the night sky on a clear evening, just as humans have done for thousands of years. The same stars that guided ancient sailors, inspired poets, and sparked the curiosity of early astronomers now twinkle above us with the same mysterious beauty. Tonight, we embark on a peaceful journey through one of humanity's most remarkable achievements, our gradual, determined climb from Earth into the infinite cosmos. For millennia, humans gazed upward with wonder and longing. The moon, our celestial companion, seemed close enough to touch yet impossibly distant. The planets wandered mysteriously across the star-filled canvas of night, earning their name from the Greek word for wanderers. Ancient civilizations built monuments aligned with celestial bodies, understanding that something profound connected Earth to the heavens above. The dream of flight itself began in these quiet moments of stargazing. From Icarus to Leonardo da Vinci's flying machines, from Jules Verne's lunar cannon to H.G. Wells' time machine, humanity's imagination soared long before our rockets did. But it would take the convergence of scientific understanding, technological innovation, and the peculiar pressures of the 20th century to transform these ancient dreams into gleaming reality. As you settle into comfort, let your mind drift back to October 4th, 1957, a date that would forever change humanity's relationship with the cosmos above. Chapter 1. The beeping that changed the world. Sputnik's legacy. Picture a crisp autumn evening in Moscow, 1957. In a secret facility, engineers and scientists huddle around radio equipment, their faces illuminated by the warm glow of vacuum tubes and oscilloscope screens. They're listening intently for something that has never been heard before, a radio signal transmitted from space. Then it comes, beep, beep, beep. A simple, rhythmic tone that would echo around the world and announce humanity's entry into the space age. Sputnik 1, a polished sphere barely larger than a beach ball, orbited Earth every 96 minutes. Its radio transmitters sending that iconic signal down to a planet suddenly awakened to new possibilities. The spacecraft itself was elegantly simple, a 184-pound aluminum sphere with 4 whip-like antennas extending from its surface. Inside, radio transmitters powered by batteries sent their signals earthward, while the sphere's polished surface reflected sunlight, making it visible to observers below as it traced its path across the twilight sky. But Sputnik was more than a technological achievement. It was a profound shift in human consciousness. For the first time in our species' history, we had placed an artificial object in orbit around our planet. The invisible chains of gravity that had bound us since the dawn of time had been broken, if only for one small beeping sphere. The world's reaction was immediate and intense. In the United States, people gathered in their backyards, craning their necks skyward to catch a glimpse of this new artificial star. Radio operators tuned their receivers to 20.005 and 40.002 MHz to hear Sputnik's call from the void. Children who heard that beeping would grow up to become the engineers, scientists, and astronauts who would walk on the moon. The Soviet success sparked what we now call the space race. But in those quiet moments of 1957, as families stood in their gardens listening to a radio signal from orbit, it was something more profound. It was the moment humanity first reached beyond its cradle and touched the infinite. Just 1 month later, the Soviets launched Sputnik 2, carrying a small dog named Laika. This gentle creature became the first living being to orbit Earth, her heartbeat and breathing monitored by instruments, as she sailed silently above the clouds. Though Laika's journey ended in space, her legacy lived on in every space mission that followed. She showed that life could exist beyond Earth's atmosphere, paving the way for human spaceflight. As winter settled over the launch sites of both superpowers, engineers worked tirelessly in the cold, their breath visible in the frigid air as they prepared humanity's next steps into the cosmos. The beeping of Sputnik had awakened something deep within our species, a calling that would not be silenced until we had walked among the stars themselves. The early satellites that followed were increasingly sophisticated. Explorer 1, America's first successful satellite, discovered the Van Allen radiation belts surrounding Earth, invisible rivers of charged particles trapped by our planet's magnetic field. These discoveries reminded us that space was not empty, but filled with phenomena we were only beginning to understand. Each launch built upon the last, like chapters in an unfolding story. The rockets grew larger, the satellites more complex, and our understanding deeper. In the quiet control rooms of both nations, engineers plotted trajectories and calculated orbital mechanics, their slide rules and early computers helping to chart courses through the three-dimensional ocean of space. Chapter 2. Pioneers in the Void, the Human Journey begins. Imagine the profound silence that greets the first human being to leave Earth's atmosphere. On April 12, 1961, Yuri Gagarin experienced a solitude no human had ever known, the complete, enveloping quiet of space, broken only by the hum of his spacecraft's life support systems and the occasional crackle of radio communications from the distant ground below. Gagarin's journey aboard Vostok 1 lasted just 108 minutes. But in that brief span, he became something entirely new in human history: a space traveler. As his spherical capsule orbited Earth at 17,500 miles per hour, Gagarin looked out through small portholes at a view that would forever change our perspective of home. "The Earth is blue," he radioed back, his voice calm despite the magnitude of the moment. "How wonderful! It is amazing." Below him, the curve of our planet revealed itself in a way no human had ever seen. A brilliant blue marble suspended in the infinite black of space, with swirling white clouds and the thin, gossamer line of atmosphere that protects all life. The technology that carried Gagarin to space was both sophisticated and elegantly simple. The Vostok spacecraft consisted of two main sections: a spherical descent module where Gagarin sat during launch and landing, and a service module containing life support equipment and retro-rockets. The entire craft was designed for a single orbit, a gentle dip into the cosmic ocean before returning safely home. 3 weeks later, on May 5, 1961, Alan Shepard became the first American in space aboard Freedom 7. His suborbital flight lasted just 15 minutes, but those quarter hours were filled with the wonder of weightlessness and the breathtaking view of Earth's curvature. Shepard's calm professionalism during the flight, including his famous "Why don't you fix your little problem and light this candle?" comment during a launch delay, epitomized the test pilot mentality that would carry humans to the moon. These early flights were tentative steps, like a child learning to walk. Each mission pushed a little further, stayed up a little longer, and tested new systems. Gurman Titov spent an entire day in space aboard Vostok 2, experiencing multiple sunrises and sunsets as he orbited Earth 17 times. He was the first to sleep in space, to eat in space, and to experience space sickness, the queasy feeling that affects many astronauts as their bodies adapt to weightlessness. The Mercury program that followed Shepard's flight was a careful progression of increasingly ambitious missions. John Glenn's three-orbit flight aboard Friendship 7 in February 1962 captivated the world as America watched their astronauts circle the globe. Glenn's observations of the fireflies outside his window, later determined to be ice crystals illuminated by sunlight, reminded everyone that space held surprises and wonders yet to be discovered. As these early space travelers shared their experiences, a new vocabulary entered human language. They spoke of the profound silence of space, of Earth's impossibly thin atmosphere, and of the strange sensation of floating freely in 3 dimensions. Weightlessness, they discovered, was not the absence of weight but rather the constant sensation of falling, a perpetual gentle tumble that lasted as long as they remained in orbit. The spacecraft of this era were marvels of engineering simplicity. Life support systems recycled air and removed carbon dioxide using chemical scrubbers. Food came in tubes and bite-sized cubes. Communication with Earth required precisely timed radio passes as the spacecraft swept around the planet. Every system was designed with redundancy in mind, because in space, there was no possibility of rescue or repair. Soviet cosmonauts and American astronauts pushed the boundaries further with each flight. Alexei Leonov took humanity's first steps outside a spacecraft during a spacewalk in March 1965, floating at the end of a tether as Earth turned slowly below him. His space suit ballooned in the vacuum, making his return to the airlock a struggle that nearly ended in tragedy, a reminder that space exploration was still an inherently dangerous endeavor. Chapter 3: Rendezvous in the Cosmic Dance, Learning to Meet in Space. In the gentle darkness of space, two spacecraft approach each other with the delicate precision of dancers. This scene, which would become routine decades later, represented one of the most challenging achievements of early space exploration: orbital rendezvous and docking. Before humans could journey to the moon, they first had to learn how to find each other in the vast three-dimensional ocean of space. The Gemini program, America's bridge between the single-seat Mercury capsules and the three-person Apollo spacecraft, was designed to master the intricate choreography of spaceflight. Gemini spacecraft were roomier than their Mercury predecessors, with two astronauts sitting side by side in seats that could be adjusted for different mission requirements. These missions would teach NASA how to change orbits, how to rendezvous with other spacecraft, how to dock two vehicles together, and how to work outside in the vacuum of space. Gemini 6 and Gemini 7 achieved the first rendezvous in December 1965, with the two spacecraft approaching to within 1 foot of each other as they orbited Earth together. The astronauts could see each other through their windows, waving across the void in a moment that was both technically profound and beautifully human. They had proven that spacecraft could find each other in space, a capability essential for lunar missions that would require docking with command modules orbiting the moon. The Soviet Union pursued their own rendezvous program with characteristic ambition. Their Soyuz spacecraft, which first flew in 1967, was designed for longer duration missions and featured an orbital module that provided additional living space for crews. The Soyuz design was so successful that variants of it continue to carry astronauts to space today, making it the longest-serving spacecraft design in history. Spacewalking, or EVA, extravehicular activity, evolved from terrifying first attempts to routine operations during the Gemini program. Ed White's spacewalk during Gemini 4 lasted 23 minutes, with the astronaut floating at the end of a golden tether, using a small maneuvering unit to move around his spacecraft. His reluctance to return inside, "This is the greatest experience, it's just tremendous," captured the wonder that space travelers felt when freed from the confines of their capsules. The technical challenges of EVA were immense. Spacesuits had to provide life support, protection from radiation and micrometeoroids, and enough flexibility for astronauts to work with their hands. The suits were essentially one-person spacecraft, complete with communications, life support, and thermal control systems. Early suits were connected to the spacecraft by umbilicals that provided air, power, and communications, creating a literal lifeline between the astronaut and safety. During these training missions, astronauts learned to work with tools in weightlessness, discovering that every action produced an equal and opposite reaction. Trying to turn a bolt might spin the astronaut instead of the bolt. Tasks that seemed simple on Earth became complex choreographed movements in space. These lessons would prove invaluable when humans finally reached the moon and needed to work efficiently in alien environments. The longest Gemini mission, Gemini 7, lasted 2 weeks, long enough to simulate a journey to the moon and back. Frank Borman and James Lovell lived in a space no larger than the front seat of a small car, learning how human beings adapted to extended spaceflight. They discovered that the human body was remarkably adaptable to weightlessness, though it came with challenges. Bone density decreased, muscles atrophied, and fluids shifted toward the head, causing the puffy-faced appearance common to space travelers. As the Gemini program concluded, NASA had achieved all the major objectives needed for lunar missions. They had proven that humans could live and work in space for 2 weeks, that spacecraft could rendezvous and dock, that astronauts could work outside their vehicles, and that precise orbital maneuvers could be performed on demand. The stage was set for humanity's greatest adventure, leaving Earth orbit entirely and traveling to another world. Chapter 4. The Eagle has landed. Apollo's Lunar Symphony. Picture the surface of the Moon on July 20, 1969. A landscape of ancient dust and rock, bathed in the harsh light of an airless world. No wind has stirred this dust for millions of years. No rain has fallen. No life has ever disturbed the perfect preservation of impact craters formed when the solar system was young. Into this profound silence comes the gentle whisper of rocket engines as a strange, angular craft descends from the black sky above. The Apollo 11 lunar module Eagle, carrying Neil Armstrong and Buzz Aldrin, touched down in the Sea of Tranquility with just 25 seconds of fuel remaining. Armstrong's calm voice crackled across the 240,000 miles to Earth. The Eagle has landed. At that moment, 2 human beings sat in a fragile aluminum spacecraft on the surface of another world, farther from home than anyone had ever traveled. The journey to this moment had begun with President Kennedy's bold declaration in 1961. "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the Moon and returning him safely to the Earth." It seemed impossible at the time. America had barely managed to put a single astronaut into orbit. Yet in 8 years, through the dedicated work of over 400,000 people, that impossible dream became reality. The Apollo spacecraft was a marvel of engineering elegance. The command module, where the 3 astronauts lived during most of their journey, was a cone-shaped capsule with a heat shield designed to protect them during their fiery return to Earth's atmosphere. The service module attached behind it contained fuel, life support, and the main engine needed for course corrections and lunar orbit insertion. Together, these formed the Command and Service Module (CSM) that would carry the crew to the Moon and back. The lunar module was perhaps even more remarkable, a specialized spacecraft designed to operate only in the vacuum of space and on the Moon's surface. It consisted of 2 stages: the descent stage, which contained the landing engine and fuel, and the ascent stage, which would carry the astronauts back to lunar orbit after their surface operations. The LM was so specialized for its environment that it could never return to Earth. It was built for the alien conditions of space and the Moon alone. The Saturn V rocket that carried these spacecraft was the most powerful rocket ever successfully flown, standing 363 feet tall and weighing 6.2 million pounds when fully fueled. Its first stage alone generated 7.5 million pounds of thrust, equivalent to the power of 85 Hoover dams concentrated into a controlled explosion lasting just 2.5 minutes. The sound of a Saturn V launch could be heard 100 miles away, and the vibrations registered on seismographs across the country. Armstrong and Aldrin's first steps on the lunar surface were broadcast live to an estimated 650 million people, nearly 1/5 of the world's population at the time. As Armstrong descended the LM's ladder, his words entered history. "That's one small step for man, one giant leap for mankind." The grainy black and white images showed a bulky figure in a white spacesuit moving with the slow, bouncing gait imposed by the Moon's 1/6 gravity. The lunar surface they explored was unlike anything on Earth. The soil, called regolith, was ground to a fine powder by billions of years of meteorite impacts. It clung to everything, sparked when kicked, and left dark footprints that would remain visible for millions of years in the airless environment. The horizon was surprisingly close, just 1.5 miles away, due to the Moon's smaller size and beyond it lay the absolute black of space. During their 21 hours on the surface, Armstrong and Aldrin collected 47.5 pounds of lunar samples, conducted scientific experiments, and planted an American flag. But perhaps their most important cargo was their changed perspective. They had seen Earth rise over the lunar horizon, a small, blue, living world suspended in the cosmic dark. This image, photographed during Apollo 8's lunar orbit mission the previous December, showed humanity our planet as it truly was, a tiny oasis of life in an infinite universe. The return journey was equally miraculous. The LM's ascent stage fired its engine flawlessly, lifting the two astronauts off the lunar surface to rendezvous with Michael Collins, who had been orbiting the moon alone in the command module. The docking was performed with the precision of ballet, bringing the crew together for their journey home. 3 days later, they splashed down in the Pacific Ocean, completing humanity's first round trip to another world. 5 more Apollo missions followed, each pushing the boundaries of exploration further. Apollo 12 demonstrated precision landing capabilities by touching down within walking distance of the unmanned Surveyor 3 probe. Apollo 14 saw Alan Shepard, America's first astronaut, hit golf balls on the lunar surface, watching them arc much farther in the low gravity than they ever could on Earth. Apollo 15, 16, and 17 carried lunar rovers, allowing astronauts to travel miles from their landing sites and explore the moon's mountains, valleys, and ancient impact craters. The final Apollo mission, Apollo 17 in December 1972, carried the only scientist astronaut to walk on the moon, geologist Harrison Schmitt. His trained eye identified orange soil that told the story of ancient lunar volcanism, adding to our understanding of how the moon formed and evolved. Eugene Cernan, the mission commander, became the last human to leave footprints on the lunar surface, promising as he departed, "We shall return." Chapter 5, Bridging Earth and Space, the Space Shuttle Era. Imagine a spacecraft that takes off like a rocket but lands like an airplane, reusable and elegant, designed to make space travel as routine as commercial aviation. This was the dream behind the Space Shuttle program, to create a truck for hauling cargo and cruise to orbit, a versatile workhorse that would open space to regular human activity. On April 12, 1981, exactly 20 years after Yuri Gagarin's first spaceflight, Space Shuttle Columbia lifted off from Kennedy Space Center with astronauts John Young and Robert Crippen aboard. Unlike the ballistic capsules that had carried all previous space travelers, Columbia was designed to be piloted during both ascent and landing. The shuttle's crew could steer their craft through the atmosphere and touch down on a runway, just like a conventional aircraft. The Space Shuttle system was unlike anything that had flown before. The orbiter itself, the airplane-like vehicle most people think of as the shuttle, was attached to a large external fuel tank that fed its 3 main engines during the 8.5-minute climb to orbit. 2 solid rocket boosters provided additional thrust during the first 2 minutes of flight, then separated and parachuted into the ocean for recovery and reuse. It was engineering ballet performed with millions of pounds of thrust and temperatures hot enough to melt steel. The shuttle's cargo bay was spacious enough to carry entire satellites, space telescopes, or laboratory modules. Its robotic arm, officially called the Canadarm, could delicately manipulate payloads weighing several tons, positioning them with the precision of a surgeon's hands. For the first time, astronauts could deploy, repair, and retrieve satellites, making space a place where humans could work rather than merely visit. 5 shuttle orbiters were built: Columbia, Challenger, Discovery, Atlantis, and Endeavour. Each had its own personality and history. Columbia, the Pathfinder, flew the first mission and many test flights. Discovery became the workhorse of the fleet, flying more missions than any other orbiter. Atlantis specialized in missions to the Russian space station Mir and later the International Space Station. Endeavour, Built to replace the lost Challenger, incorporated lessons learned from years of shuttle operations. The shuttle program democratized space travel in ways the Apollo program never could. It carried not just military test pilots and engineers, but teachers, doctors, scientists, and international crew members. In 1983, Sally Ride became the first American woman in space aboard Challenger. Guyon Bluford Jr. became the first African-American astronaut in space the same year. The shuttle's larger crew compartments could accommodate up to 8 people, creating a genuine community in orbit. One of the shuttle's most remarkable achievements was the deployment and servicing of the Hubble Space Telescope. Launched aboard Discovery in 1990, Hubble initially suffered from blurred vision due to a flaw in its primary mirror. Rather than abandon the $2.5 billion observatory, NASA planned an ambitious repair mission. In December 1993, Endeavour's crew performed a series of complex spacewalks to install corrective optics, essentially giving Hubble contact lenses. The mission's success transformed Hubble from an embarrassment into one of humanity's greatest scientific instruments. The shuttle also served as a construction platform for the International Space Station. Beginning in 1998, shuttle crews delivered modules, solar arrays, life support systems, and scientific equipment to build humanity's largest and most complex space structure. The station grew piece by piece over more than a decade, with shuttle crews performing the delicate work of assembly in the vacuum of space. Shuttle missions routinely included multiple spacewalks, giving astronauts extensive experience working outside their spacecraft. The shuttle's spacious airlock could accommodate 2 fully suited astronauts, and its cargo bay provided a stable platform for EVA operations. Astronauts learned to work with sophisticated tools, install complex equipment, and perform repairs on orbital structures. These skills would prove essential for building and maintaining the International Space Station. The program also advanced our understanding of how humans adapt to extended spaceflight. Shuttle missions typically lasted 1 to 2 weeks, allowing researchers to study how the human body responds to weightlessness. They discovered that astronauts lose bone density, experience muscle atrophy, and suffer fluid shifts that affect their cardiovascular systems. These findings informed the design of exercise equipment and medical protocols for long-duration missions. Despite its successes, the shuttle program faced 2 tragic setbacks. Challenger was lost in January 1986 when a seal failure in one of its solid rocket boosters caused an explosion 73 seconds after launch, killing all 7 crew members including teacher Krista McAuliffe. Columbia was lost during re-entry in February 2003 when damage to its heat shield, caused by foam debris during launch, led to the vehicle's breakup over Texas. These losses reminded everyone that spaceflight remained inherently dangerous despite decades of apparent routine. The Space Shuttle program concluded in July 2011 with Atlantis's final landing. Over 30 years, the 5 orbiters had flown 135 missions, carried 355 people into space, deployed countless satellites, built the International Space Station, and serviced the Hubble Space Telescope multiple times. More than any other program, the shuttle made space feel accessible and routine, paving the way for the commercial space ventures that followed. Chapter 6. The Red Planet Beckons. Mars Exploration Unfolds. In the pre-dawn darkness of a Florida morning in 1975, 2 identical spacecraft sat atop Titan III rockets, ready to begin humanity's most ambitious robotic exploration of another planet. Viking 1 and Viking 2 were not just probes or orbiters. They were complete planetary exploration systems, each consisting of an orbiter to map Mars from above and a lander to touch down on its rusty surface and search for signs of life. Mars had captivated human imagination for centuries. The planet's red color earned it association with war and mystery in ancient cultures, while telescopic observations in the 19th and early 20th centuries seemed to reveal canals and seasonal changes that suggested the presence of intelligent life. By the 1970s, earlier robotic missions had revealed a more complex reality. Mars was a world of massive volcanoes, deep canyons, and ancient riverbeds that spoke of a watery past dramatically different from its current cold, dry state. The Viking mission represented a quantum leap in interplanetary exploration. Each lander was equipped with sophisticated scientific instruments, including a robotic arm to collect soil samples, cameras to photograph the landscape, and biological laboratories to test Martian soil for signs of microbial life. The orbiters carried high-resolution cameras and spectrometers to map the planet's surface and atmosphere in unprecedented detail. On July 20, 1976, exactly 7 years after Apollo 11's lunar landing, Viking 1's lander separated from its orbiter and began its descent through Mars's thin atmosphere. Protected by a heat shield and slowed by parachutes and retro-rockets, it touched down safely on Chryse Planitia, a smooth plane chosen for its apparent safety. Within minutes, the lander's cameras began transmitting the first clear images ever taken from Mars's surface. The landscape that appeared on screens at NASA's Jet Propulsion Laboratory was both alien and strangely familiar. A rocky desert stretched to the horizon under a butterscotch sky, with scattered boulders casting sharp shadows in the thin atmosphere. The soil was indeed red, colored by iron oxide rust, that had formed over billions of years as the planet's iron-rich rocks were exposed to oxygen and water. It was a world that looked ancient and weathered, shaped by processes similar to those on Earth but operating under very different conditions. Viking 2 landed 2 months later in Utopia Planitia, revealing a different but equally fascinating landscape. Together, the 2 landers operated for years beyond their planned 90-day missions, monitoring weather patterns, analyzing soil composition, and searching for signs of life. The biological experiments produced tantalizing but ultimately inconclusive results. Chemical reactions that could have been caused by life, but were more likely the result of the planet's oxidizing soil chemistry. The Viking orbiters revolutionized our understanding of Mars's history and geology. They revealed Olympus Mons, a shield volcano 3 times taller than Mount Everest and roughly the size of Arizona. They mapped Valles Marineris, a canyon system that would stretch across the entire United States if placed on Earth. Most significantly, they photographed clear evidence of ancient water flow, branching valley networks, outflow channels, and floodplains that told the story of a Mars that was once warm and wet. For nearly 2 decades after Viking, Mars remained unvisited by new landers, though orbiters continued to map the planet from above. The Mars Global Surveyor, launched in 1996, used laser altimetry to create detailed topographic maps showing that Mars had distinct northern and southern hemispheres, smooth lowlands in the north and ancient, cratered highlands in the south, possibly indicating that an ocean once covered much of the northern hemisphere. The next generation of Mars exploration began with the Mars Pathfinder mission in 1997. Unlike the stationary Viking landers, Pathfinder deployed a small rover named Sojourner that could drive around the landing site, analyzing rocks and soil with its suite of instruments. The size of a microwave oven and weighing just 23 pounds, Sojourner proved that mobile robots could operate effectively on Mars, paving the way for much larger and more capable rovers. Sojourner's landing site in Ares Vallis was chosen specifically because it appeared to be an ancient floodplain where water had deposited rocks from across a wide region of Mars. The little rover analyzed these rocks, finding compositions that suggested Mars had once had a thicker atmosphere and liquid water on its surface. Images from the lander showed morning frost forming on the Martian surface and dust devils dancing across the plains, bringing Mars to life in ways that static images never could. The twin Mars exploration rovers, Spirit and Opportunity, launched in 2003 with far more ambitious goals. Each rover was the size of a golf cart and equipped with sophisticated analytical instruments, including spectrometers, microscopic imagers, and rock abrasion tools that could grind into Martian rocks to analyze their interiors. Designed for 90-day missions, both rovers operated for years beyond their planned lifetimes, with Opportunity continuing to explore Mars for nearly 15 years. Spirit landed in Gusev Crater, thought to be an ancient lake bed, while Opportunity landed on Meridiani Planum, where orbital spectrometers had detected minerals that form in the presence of water. Both rovers found compelling evidence that Mars had been warm and wet in its ancient past. Opportunity discovered small spherical concretions nicknamed blueberries that had formed in standing water, while Spirit found evidence of ancient hot springs and hydrothermal activity. The rover's most profound contribution was making Mars feel like a real place rather than an abstract destination. Their daily images showed changing weather, shifting sand dunes, and the slow progression of Martian seasons. When Spirit became stuck in soft soil, the mission team spent months trying to free it, creating an emotional connection between Earth and a robot millions of miles away. When Opportunity finally succumbed to a global dust storm in 2018, NASA's last communication attempt was met with silence, ending one of the most successful robotic missions in history. Chapter 7: The Curiosity to Persevere Modern Mars Exploration. Picture a robot the size of a small car slowly traversing the floor of an ancient crater on Mars, its 6 wheels crunching softly through rust-colored soil that hasn't been disturbed for millions of years. This is Curiosity, humanity's most sophisticated Mars explorer, continuing a story of robotic discovery that began with simple landers and evolved into mobile laboratories capable of analyzing the red planet's geology, atmosphere, and potential for life. Curiosity landed in Gale Crater on August 5, 2012, using a revolutionary sky crane system that lowered the rover gently to the surface on cables while rocket engines hovered overhead. This dramatic landing method was necessary because Curiosity, weighing 899 pounds, was too heavy for the airbag landing system used by earlier rovers. The successful landing proved that even more ambitious missions to Mars were possible. Gale Crater was chosen as Curiosity's destination because it contained a mountain of layered sediments, formerly named Elis Mons but nicknamed Mount Sharp, that recorded billions of years of Martian history. Like reading pages in a book, Curiosity could drive up the slopes of this mountain, analyzing different layers to understand how Mars's climate had changed over time. Each rock layer was a snapshot of ancient environmental conditions, preserved in stone. The rover's scientific capabilities were unprecedented. It carried a laser that could vaporize rocks from a distance, allowing spectrometers to analyze their composition without the rover having to drive to each target. A drill could bore into rocks to collect powdered samples for analysis by internal laboratories. Cameras could take microscopic images of rock textures and panoramic views of the landscape. A weather station monitored daily conditions, and radiation detectors measured the cosmic ray environment that future human explorers would face. Curiosity's discoveries revolutionized our understanding of ancient Mars. In its first year, the rover found evidence that Gale Crater had once contained a lake of drinkable water, not too acidic, not too salty, with the right chemical conditions to support microbial life if any had existed. The rocks showed clear signs of flowing water, rounded pebbles that had been tumbled by streams, cross-bedding patterns created by ancient currents, and minerals that could only form in the presence of liquid water. As Curiosity climbed the lower slopes of Mount Sharp, it discovered that Mars's climate had changed dramatically over time. Lower, older layers showed evidence of neutral pH water that could have supported life, while higher, younger layers indicated increasingly acidic conditions as Mars lost its atmosphere and dried out. The rover was reading the planet's biography written in stone, revealing the story of a world that had transformed from potentially habitable to the cold, dry desert we see today. The rover also made unexpected discoveries about Mars's current activity. It detected seasonal variations in atmospheric methane, a gas that on Earth is often produced by living organisms. While the source of Martian methane remains mysterious, it could be geological or biological. Its presence showed that Mars was not the static, dead world many had assumed. The planet was still active, still changing, still capable of surprises. In 2021, Curiosity was joined by Perseverance, an even more ambitious rover designed specifically to search for signs of ancient microbial life. Landing in Jezero Crater, site of an ancient river delta, Perseverance carried the most sophisticated suite of instruments ever sent to another planet. Its main mission was not just to analyze rocks, but to collect samples that would eventually be returned to Earth for detailed study in laboratories. Perseverance's landing was another technological marvel. The sky crane system that had worked for Curiosity was refined and improved, allowing the new rover to land within 1.2 miles of its target, precision that would have been impossible with earlier landing systems. The landing was broadcast live on Earth, with images from the rover showing its parachute deploying and the sky crane lowering it to the surface. The rover carried a small helicopter named Ingenuity, which achieved the first powered flight on another planet. Originally designed for just 5 flights as a technology demonstration, Ingenuity flew dozens of times, scouting terrain ahead of Perseverance and proving that aerial exploration of Mars was not only possible but valuable. Its flights opened up entirely new possibilities for future Mars exploration, potentially allowing rovers to explore terrain that would be impossible to reach by ground. Perseverance's search for ancient life focused on the rocks of Jezero Crater's delta, where a river had once deposited sediments rich in organic compounds and minerals that could preserve signs of ancient microbes. The rover used ground-penetrating radar to peer into the subsurface, cameras to examine rock textures in minute detail, and spectrometers to identify the chemical signatures that might indicate past life. Perhaps most importantly, Perseverance was designed to prepare for human exploration of Mars. It carried MOXIE, an experiment that successfully produced oxygen from the Martian atmosphere, a technology that could provide breathable air and rocket fuel for future astronauts. The rover's weather station monitored conditions that humans would face, while its cameras documented dust storms, clouds, and other atmospheric phenomena that could affect future missions. The rover's psychological impact on Earth was as significant as their scientific discoveries. Their daily images and regular updates made Mars feel like a place humans might actually visit someday. Social media accounts for the rovers gave them personalities, making their discoveries feel personal and immediate. When Opportunity's mission ended, people around the world mourned the loss of a robot that had become humanity's representative on a distant world. Each Mars mission built upon the knowledge gained from its predecessors, creating an increasingly detailed picture of the red planet's past, present, and potential future. The progression from simple landers to sophisticated mobile laboratories demonstrated humanity's growing ability to explore other worlds robotically, preparing the way for eventual human missions to Mars. As these mechanical explorers continue their patient work, they remind us that our reach now extends far beyond our home planet, carrying our curiosity and wonder to worlds that were once only points of light in the night sky. Chapter 8: Voyager's Grand Tour Messengers to the Outer Darkness. In the summer of 1977, as Earth completed another orbit around our familiar Sun, 2 spacecraft began journeys that would take them farther from home than any human-made objects had ever traveled. Voyager 1 and Voyager 2 were launched just 16 days apart, taking advantage of a rare planetary alignment that occurs only once every 175 years, a celestial dance that would allow these robotic explorers to visit multiple worlds in the outer solar system using the gravity of each planet to propel them toward the next. The Voyager spacecraft were marvels of 1970s engineering, each weighing about as much as a small car and powered by radioisotope thermoelectric generators that converted the heat from decaying plutonium into electricity. They carried no solar panels because they were destined for regions of the solar system where sunlight is hundreds of times dimmer than on Earth. Their main communications antenna, a white dish 12 feet across, would beam discoveries back to Earth across billions of miles of empty space. Each Voyager carried a golden record, a phonograph disc containing sounds and images from Earth, intended as a message to any extraterrestrial civilization that might someday encounter these artifacts of human exploration. The records included music from Bach and Chuck Berry, greetings in dozens of languages, and the sound of rain, wind, and laughter. They were humanity's calling cards, cast into the cosmic ocean with hopes that someday, perhaps millions of years in the future, another intelligence might discover them and know that we once existed. Voyager 1's first major encounter was with Jupiter in March 1979. As the spacecraft approached the giant planet, it revealed a world of stunning complexity and beauty. Jupiter's great red spot, a hurricane larger than Earth that had been raging for centuries, appeared in exquisite detail. The planet's faint ring system, unknown before Voyager's arrival, emerged from the data as a gossamer circle of dust and ice particles. Most surprisingly, Jupiter's 4 largest moons proved to be worlds in their own right, each unique and fascinating. Io, the innermost large moon, astonished scientists with active volcanoes spewing sulfur compounds hundreds of miles into space. The moon's surface was painted in brilliant yellows, reds, and oranges by sulfur deposits from these volcanic eruptions. Here was a world more volcanically active than Earth, heated by the gravitational tides raised by massive Jupiter. Europa, the next moon outward, showed a surface of cracked ice that suggested a liquid ocean beneath, an ocean that might contain more water than all of Earth's seas combined. Voyager 2 followed 4 months later, providing additional observations of the Jovian system and then continuing onward to Saturn. When both spacecraft reached the ringed planet in 1980 and 1981, they revealed the ring system to be far more complex than anyone had imagined. Instead of the simple bands visible from Earth, Saturn's rings proved to be composed of thousands of individual ringlets, some twisted into braids, others held in place by tiny shepherd moons that gravitationally corralled the ring particles. Saturn's moon Titan, larger than the planet Mercury, emerged as one of the most intriguing worlds in the solar system. Shrouded in a thick, orange atmosphere composed primarily of nitrogen with traces of methane, Titan remained mysterious behind its opaque haze. Voyager's instruments detected organic compounds in the atmosphere, the building blocks of life, suggesting that this distant moon might harbor environments relevant to understanding how life might arise elsewhere in the universe. At Saturn, the 2 Voyagers' paths diverged. Voyager 1 was programmed to make a close flyby of Titan, an encounter that bent its trajectory upward relative to the plane of the solar system, sending it on a path toward interstellar space. Voyager 2 continued onward to Uranus and Neptune, becoming the only spacecraft ever to visit these distant ice giants. The encounter with Uranus in January 1986 revealed a world lying on its side, rotating with its poles nearly in the plane of its orbit. This strange orientation meant that each pole experienced 42 years of continuous sunlight followed by 42 years of darkness, as the planet completed its 84-year orbit around the Sun. Uranus's magnetic field was tilted at a crazy angle relative to its rotation axis, suggesting that the planet had suffered a collision with another large body in its ancient past. Voyager 2's final planetary encounter came at Neptune in August 1989, nearly 12 years after launch. Neptune, the most distant planet from the Sun, proved to be surprisingly active for such a cold world. Winds in its atmosphere reached speeds of up to 1,200 miles per hour, the fastest in the solar system. The planet's largest moon, Triton, orbited backward relative to Neptune's rotation and showed signs of active geysers spouting nitrogen gas and dark particles high into the thin atmosphere. With their planetary missions complete, both Voyagers continued outward, carrying their instruments into the realm beyond the planets. They became humanity's first probes of interstellar space, designed to study the boundary between our solar system and the vast spaces between the stars. In 2012, Voyager 1 crossed the heliopause, the edge of the solar wind's influence, and entered interstellar space for the first time in human history. The data streaming back from this boundary region revealed that interstellar space was not empty. It contained magnetic fields, cosmic rays, and charged particles from other star systems. The Voyagers discovered that our solar system exists within a bubble of charged particles blown outward by the solar wind, and that this bubble moves through a galaxy filled with similar bubbles from other stars. Even now, decades after launch, both Voyagers continue to transmit data back to Earth, though their power sources are gradually weakening. Their signals, taking hours to reach Earth across the vast distances of space, carry information about regions no human has ever explored. They are our most distant ambassadors, still functioning after traveling for more than 4 decades through the harsh environment of space. The Voyager missions transformed our understanding of the outer solar system from abstract knowledge into vivid reality. They showed us worlds of incredible diversity and beauty: volcanic moons, icy oceans, complex ring systems, and atmospheric phenomena beyond anything found on Earth. Most importantly, they demonstrated that even with 1970s technology, humanity could successfully explore the farthest reaches of our solar system, paving the way for future missions to these distant worlds. Chapter 9: Windows to the Universe, the Hubble Space Telescope Revolution. Imagine floating 340 miles above Earth's surface, beyond the turbulent atmosphere that has limited ground-based astronomy since humans first looked up at the stars. Here, in the perfect vacuum of space, a silver telescope the size of a school bus slowly rotates to point its mirror toward distant galaxies, its instruments gathering light that has traveled billions of years to reach this moment of discovery. The Hubble Space Telescope, launched aboard Space Shuttle Discovery in April 1990, was conceived as humanity's first great observatory in space. Free from the blurring effects of Earth's atmosphere, Hubble was designed to see deeper into space and further back in time than any telescope before it. Its 2.4-meter primary mirror could theoretically resolve details as fine as reading a newspaper from 25 miles away, while its position above the atmosphere would allow it to observe in ultraviolet and infrared wavelengths that never reach Earth's surface. But Hubble's story began with disappointment. Within weeks of its deployment, astronomers discovered that the telescope's primary mirror had been ground to the wrong shape, a flaw smaller than 1/50th the width of a human hair, but enough to blur its images significantly. Instead of the sharp, detailed views expected, Hubble's first pictures were only marginally better than ground-based telescopes. The media dubbed it the Hubble trouble, and critics questioned whether the billion-dollar observatory would ever fulfill its promise. The solution came in December 1993, when Space Shuttle Endeavour carried a crew of 7 astronauts on one of the most complex repair missions ever attempted. During 5 spacewalks totaling more than 35 hours, the crew installed a set of corrective optics called COSTAR, Corrective Optics Space Telescope Axial Replacement, that acted like contact lenses for Hubble's flawed vision. They also replaced the telescope's main camera with one that had built-in corrections for the mirror's aberration. When Hubble's first corrected images were released in January 1994, they exceeded everyone's wildest expectations. The telescope could now see details in galaxies, nebulae, and star clusters with unprecedented clarity. A globular cluster that had appeared as a fuzzy ball in ground-based telescopes resolved into hundreds of thousands of individual stars. Galaxies revealed intricate spiral arms, star-forming regions, and evidence of supermassive black holes at their centers. One of Hubble's most famous contributions to astronomy came through the Hubble Deep Field observations. In 1995, astronomers pointed the telescope at what appeared to be an empty patch of sky no larger than a grain of sand held at arm's length. They collected light for 10 days, building up an image of the faintest, most distant objects visible. The resulting picture revealed nearly 3,000 galaxies in this tiny region of space, each containing billions of stars. This single image revolutionized our understanding of the universe's scale and contents. The deep field observations showed galaxies as they appeared billions of years ago, when the universe was young. Some appeared as strange, irregular shapes unlike the elegant spirals and ellipticals seen in the nearby universe. These ancient galaxies were caught in the act of formation, colliding and merging to create the larger, more organized structures we see today. Hubble had become a time machine, showing us cosmic history preserved in light. Hubble's observations of nearby objects proved equally revolutionary. The telescope discovered that jets of gas from young stars could stretch for trillions of miles across space, sculpting the gas and dust from which new stars form. In the Orion Nebula, Hubble revealed disk-shaped structures around young stars that appeared to be planetary systems in the process of formation, direct evidence that planets might be common throughout the galaxy. The telescope studies of our own solar system provided new insights into familiar worlds. Hubble tracked storms on Mars, monitored changes in Jupiter's atmosphere, and discovered new moons around distant planets. When comet Shoemaker-Levy 9 collided with Jupiter in 1994, Hubble captured images of the impacts, showing dark bruises in Jupiter's atmosphere larger than Earth that persisted for months after the collisions. Perhaps Hubble's most profound discovery involved the expansion of the universe itself. By observing distant supernovae, exploding stars that serve as cosmic lighthouses, Hubble helped astronomers determine that the universe's expansion is actually accelerating. This discovery led to the realization that some mysterious dark energy makes up about 68% of the universe, driving galaxies apart at an ever-increasing rate. The discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of cosmic evolution. Hubble's longevity has been maintained through 5 servicing missions performed by Space Shuttle crews. Astronauts replaced gyroscopes, installed new instruments, upgraded computers, and even replaced entire camera systems while the telescope orbited Earth. These servicing missions demonstrated the value of human spaceflight for maintaining complex space-based observatories, allowing Hubble to remain at the forefront of astronomical research for more than 3 decades. The telescope's imaging capabilities have made it as much a cultural icon as a scientific instrument. Hubble's pictures of colorful nebulae, distant galaxies, and exotic phenomena have appeared in countless books, documentaries, and museum exhibitions. The famous Pillars of Creation image from the Eagle Nebula shows towering columns of gas and dust where new stars are being born, combining scientific insight with breathtaking beauty. These images have inspired millions of people to consider their place in the cosmos. As Hubble continues to operate in its 4th decade, it works alongside newer space telescopes that observe in different wavelengths of light. Together, they provide a comprehensive view of the universe from the radio waves emitted by cold gas clouds to the high-energy X-rays produced by black holes and neutron stars. Hubble remains unique for its ability to take extremely sharp images in visible light, the same wavelengths our eyes can see. The telescope's legacy extends far beyond its scientific discoveries. Hubble demonstrated that space-based observatories could operate reliably for decades, paving the way for even more ambitious projects. Its success story, from initial failure to triumphant recovery to ongoing discoveries, shows how space exploration requires patience, ingenuity, and the willingness to solve complex problems millions of miles from home. Chapter 10. A Home Among the Stars, the International Space Station. Picture a structure the size of a football field orbiting Earth every 90 minutes, its solar arrays glinting like golden wings as it catches the first rays of sunrise over the Pacific Ocean. This is the International Space Station, humanity's foothold in space and our most complex engineering achievement. Built through the cooperation of 16 nations, the ISS represents the best of human collaboration, floating 250 miles above the political boundaries that divide us on the surface below. The station's story begins in the aftermath of the Cold War, when former adversaries found common ground in their shared dreams of space exploration. The Soviet Union's Mir space station had demonstrated that humans could live and work in space for extended periods, while America's Space Shuttle program had proven the value of reusable spacecraft for assembling large structures in orbit. Combining these capabilities, engineers envisioned a space station that would surpass anything either nation could build alone. Construction of the ISS began in 1998 with the launch of Zarya, a Russian-built module that provided power and propulsion for the early station. 2 weeks later, Space Shuttle Endeavour carried Unity, an American-built connecting node, to orbit. During a complex series of spacewalks, astronauts connected these first 2 modules, beginning an assembly process that would continue for more than a decade. Each subsequent mission added new components: laboratory modules for scientific research, living quarters for the crew, solar arrays to generate power, and storage areas for supplies and equipment. The station grew like a 3-dimensional puzzle assembled in the vacuum of space, with each piece precisely manufactured on Earth and then carefully installed by spacewalking astronauts guided by robotic arms and ground-based mission controllers. The completed ISS is a marvel of international engineering. Its pressurized volume is larger than a 6-bedroom house, with modules contributed by the United States, Russia, Europe, Japan, and Canada. The station's solar arrays, with a wingspan larger than a football field, generate enough electricity to power 40 homes. Its life support systems recycle water and oxygen with such efficiency that astronauts joke about drinking their own urine from yesterday, though the recycled water is actually purer than most municipal tap water. Living aboard the ISS requires adapting to an environment where up and down have no meaning. Astronauts sleep in sleeping bags attached to walls, eat food that floats if not properly contained, and exercise on treadmills and weight machines specially designed for weightlessness. Simple tasks like washing hands or using the bathroom require careful procedures developed through decades of spaceflight experience. The station serves as humanity's premier laboratory for microgravity research. In the weightless environment of orbit, scientists can study how materials behave when freed from the effects of gravity, how flames burn without buoyancy, and how living organisms adapt to conditions impossible to replicate on Earth. Protein crystals grown in microgravity often form more perfect structures than those grown in Earth-based laboratories, potentially leading to better understanding of diseases and more effective treatments. Medical research aboard the ISS focuses on understanding how the human body adapts to long-duration spaceflight. Astronauts serve as test subjects, monitoring changes in their bone density, muscle mass, cardiovascular function, and vision. These studies are crucial for planning future missions to Mars, where astronauts will spend months in space without the possibility of rapid return to Earth if medical problems develop. The psychological aspects of long-duration spaceflight are equally important. Astronauts live in an isolated, confined environment with the same small group of people for months at a time. Mission planners study how crews interact, resolve conflicts, and maintain morale during long missions. These insights inform not only space exploration but also research into isolated environments on Earth, such as Antarctic research stations and submarine crews. Earth observation from the ISS provides unique perspectives on our planet's changing environment. Astronauts photograph everything from hurricanes and volcanic eruptions to city lights and aurora displays. Their images help scientists study climate change, track natural disasters, and monitor human impacts on the environment. The station's Earth-facing windows have been called the most expensive picture frames ever built, but the scientific value of the images they capture is immeasurable. The ISS also serves as a testbed for technologies needed for future deep space exploration. Systems for recycling water and air, generating power in space, and maintaining complex equipment far from Earth are continuously refined based on station operations. The lessons learned from keeping the ISS functioning for more than 2 decades will inform the design of spacecraft for Mars missions and lunar bases. Perhaps most importantly, the ISS demonstrates that international cooperation in space is not only possible but advantageous. Russian cosmonauts and American astronauts work side by side, joined by colleagues from Japan, Canada, and European nations. Political tensions on Earth rarely affect station operations, where crew members depend on each other for survival and success. The station has hosted visitors from dozens of countries, making space travel truly international for the first time. The station's operation requires constant supply missions from Earth. Cargo spacecraft from multiple countries deliver food, equipment, and scientific experiments while removing trash and completed research samples. Crew rotation occurs every few months, with departing astronauts passing station operations to their replacements in carefully orchestrated handovers that ensure continuity of operations. As the ISS enters its 3rd decade of operation, plans are already underway for its eventual replacement. Commercial space stations designed and operated by private companies may take over some of its functions, while governments focus on exploration missions to the Moon and Mars. The ISS has proven that humans can live and work productively in space for extended periods, paving the way for permanent human presence beyond Earth. The station's legacy extends beyond its scientific achievements to its role as a symbol of human cooperation and capability. Its construction required overcoming technical challenges that seemed insurmountable, while its operation has demonstrated that people of different nations, cultures, and languages can work together toward common goals. As Earth turns slowly beneath its orbit, the ISS reminds us that some human endeavors transcend the boundaries that divide us, reaching toward possibilities that exist only when we work together. Epilogue. The infinite journey continues. As we reach the end of our gentle journey through the history of space exploration, imagine looking up once more at the night sky, but now with eyes informed by humanity's greatest adventure. Those points of light are no longer distant mysteries but destinations we have visited, worlds we have explored, and frontiers we continue to investigate with increasingly sophisticated robotic ambassadors and human explorers. The beeping of Sputnik that began our story has evolved into a constant stream of data flowing back from spacecraft throughout the solar system and beyond. Mars rovers continue their patient geological surveys while orbital missions map the moons of Jupiter and Saturn. The Voyager spacecraft, now in interstellar space, still whisper their discoveries across the cosmic distances. New telescopes reveal exoplanets orbiting distant stars, some possibly harboring conditions suitable for life. The International Space Station continues its graceful orbit, a bright moving star visible to the naked eye as it crosses the evening sky. Aboard this outpost of humanity, astronauts from many nations conduct experiments that will inform our understanding of science, medicine, and engineering while preparing for even more ambitious journeys ahead. Commercial spacecraft now regularly carry crews to orbit, making space more accessible than ever before. Looking forward, new chapters in space exploration are already being written. Robotic missions are planning to drill through the ice of Europa and Enceladus to search for life in their hidden oceans. Sample return missions will bring pieces of Mars back to Earth for detailed analysis in laboratories worldwide. New space telescopes will search for signs of life in the atmospheres of distant worlds, while others probe the deepest mysteries of dark matter and dark energy. Human exploration is also entering a new era. Plans for permanent lunar bases would establish humanity's first foothold on another world since the Apollo missions ended. Crewed missions to Mars, once the stuff of science fiction, are now being planned with careful attention to the technical and human challenges they will present. Private companies and international partnerships are making space exploration more collaborative and sustainable than ever before. Perhaps most remarkably, the exploration of space has changed how we see ourselves and our home planet. The images of Earth taken by Apollo astronauts, enhanced by decades of satellite observations and astronaut photography, have given us a perspective on our world that was impossible before the space age. We see Earth as it truly is, a small, blue, living world in the vast cosmos, the only home we know for certain harbors life. This perspective has profound implications for how we care for our planet and each other. The astronauts who have seen Earth from space often return with a changed worldview, understanding viscerally that national boundaries are invisible from orbit and that Earth's thin atmosphere is all that protects life from the harsh environment of space. This overview effect has influenced environmentalism, international cooperation, and our understanding of humanity's place in the universe. The technologies developed for space exploration have transformed life on Earth in countless ways. Satellite communications connect the world instantaneously. GPS satellites guide our navigation. Weather satellites help predict storms and monitor climate change. Medical devices, material science, and computer technologies all bear the influence of space program innovations. The investments made in reaching for the stars have returned benefits that touch nearly every aspect of modern life. Yet perhaps the greatest legacy of space exploration is less tangible but no less real: the expansion of human consciousness and possibility. Every generation since Sputnik has grown up knowing that humans can leave Earth, that we can explore other worlds, and that the cosmos is not a distant abstraction but a realm we can investigate and understand. Children today learn about exoplanets and black holes, Mars rovers and space stations, as naturally as previous generations learned about distant countries and historical events. The story of space exploration is ultimately a story about the human spirit, our curiosity, our persistence, and our willingness to work together toward goals that transcend individual lives and national boundaries. It's about the engineers who solved seemingly impossible problems, the astronauts who risked their lives to push the boundaries of human experience, and the scientists who dedicated their careers to understanding the cosmos. As you settle into sleep tonight, carry with you the knowledge that above your head, human beings are orbiting Earth aboard the International Space Station, continuing experiments and observations that expand our understanding of science and ourselves. Robotic explorers on Mars are analyzing rocks that may contain signs of ancient life. Telescopes in space and on Earth are discovering new worlds and peering deeper into cosmic history than ever before. The beeping that started it all has become a symphony of discovery that continues to play across the solar system and beyond. Our journey from Earth into the cosmos has only just begun, and the most amazing discoveries may still lie ahead. In the quiet of night, as Earth turns beneath the stars, we can rest knowing that humanity's greatest adventure continues, carried forward by our endless curiosity and our ancient dream of touching the infinite sky above. Sleep well, fellow space travelers, aboard our beautiful spacecraft Earth as it sails through the cosmos. Tomorrow will bring new discoveries, new questions, and new reasons to look up at the stars with wonder and hope. The universe awaits, vast and full of possibilities, calling to the explorer that lives within each of us.